We're going to continue where we left off last time. So if you remember from last time, we actually talked about 4 different fundamental OS concepts. We started with the thread and talked about address spaces with translation, and then went on with process and dual mode operation, and wanted to see briefly if anybody had any questions on that. I'm actually going to continue discussing some of these a little bit in more detail. But let me just see. Boy, this is going to get really loud and annoying here. Hold on. Volume control. That probably sounds good. Wireless mic. Da-da-da-da-dum. Is that better? Can you hear me now still? Okay. Now we're not echoing in my brain, which, the voices in my head are bothering people enough. So anyway, we talked about 4 different ideas, the thread being the basic unique execution context. We can package up a series of threads in a process, and we talked about that. And part of that is we want these processes to be protected from each other, and so that's led us into talking about address spaces with translation and eventually dual mode operation. And just to bring this up, the process was kind of the key thing that we were getting at last time, and it's really an execution environment with restricted writes. It's an address space with 1 or more threads, and I'm going to show you a picture from one of the previous books there in a second. It has its own chunk of memory or address space. It has its own, it owns the file descriptors it has, and we'll start getting into that today a little bit. And it does, like I say, it's encapsulating 1 or more threads. And here's a good picture, maybe, of this. So what you see kind of at the left is what used to be called a heavyweight process or just a process in the 30 years ago. And in that situation, we basically had our address space and our protection and 1 thread. Okay, today, the thing on the right is pretty much what we call a process, which has got 3, multiple threads, many threads potentially. You always have at least 1, and notice that every thread has its own stack, its own registers, and so on, but the code, data, and files and everything are shared. Okay, so many threads, potentially 1 address space, and all have the same memory, the same code, the same data, the same everything. Okay, is that clear to everybody? Threads are encapsulated inside processes. Okay, so the other thing we talked about was how to turn 1 processor into the illusion of many processors, and the answer there was multiplexing. So we basically talked about how to take the state of a thread or process and multiplex it by loading and unloading the registers to give us this illusion as if we actually had 3 CPUs, pink, blue, and yellow. We do that with 1 processor by multiplexing them in time. Were there any questions on that idea? Okay, pretty good. Now, I promised you something last time, and we didn't quite get to it. So I wanted to say something. There was a good question about halfway through the lecture, which was sort of, does software have to do this multiplexing, or could we have hardware do it? And the answer is that, yes, you can actually design hardware to do the multiplexing for you. And there is a concept called simultaneous multithreading, which Intel has called hyperthreading. And it originally came out of the University of Washington, which is a vibrant place up near Seattle. And basically, the idea here is that it's a hardware technique for providing multiple threads with 1 set of pipeline resources. And what you see here is, I'm not going to go into this in detail, but in a typical superscalar architecture, you have a lot of things that are going on in parallel, potentially, but these dark yellow blocks show the only ones that are actually being used. The holes in here are kind of wasted potential computation. And this is what you sort of have as a modern single-threaded pipeline. In a hyper-threaded scenario over at the right, what you've actually got is 2 threads, and both threads are simultaneously loaded in the processor, so the processor has multiple register sets. And the instruction dispatching in the processor decides how to take pieces from both of the threads to fit them together and not waste any thread potential. Yeah, go ahead.
If you were supposed to explain to a 10-year-old the difference between a thread and a process, could you please do that?
Well, I would say the difference between a thread and a process is that a process contains threads. Well, it means that a process has an address space with one or more threads in it. So a process is the context. It's the chunk of memory. A thread is just the execution context. It includes a program counter and some registers. Okay, and so you put threads. Think of a process like one of those big plastic containers you get at at Costco or something, and you put threads in it, and the threads are all running in there. And so the process is the container. The threads are the actual execution context. Does that help? Good. So this technique actually works. When you buy a processor, you buy a desktop, and it's got hyper-threading, it actually has one pipeline typically with multiple threads running on the same pipeline. And then, of course, you can have multi-core, so you can have multiple processors, each of which have multiple threads running on them simultaneously. All right, you can ask me about that after class. The other thing we talked about is, if you took 152, by the way, you'd learn a lot more about that. The other thing we talked about was this dual mode, or the difference between user and kernel mode. And user mode typically is a mode that the processor runs in with more restricted resources, more restricted privileges, and kernel mode is the mode where the processor is giving full access to everything. Okay, and so there are two modes, and that means that there's at least one mode bit somewhere that has to flip from 1 to 0 and vice versa as the processor is switching back and forth. And furthermore, what's kind of interesting here is the transitions between user mode and kernel mode are very important. And so we talked about how, well, you do an exec to start a process, and we'll talk about that a little bit later. And then at the end, an exit ends the process. Or you have a system call, which comes in and out. We're going to talk about that today. Or you have an interrupt, which comes in, goes all the way down, does something with the hardware, and then eventually returns to user mode after messing with the hardware. This is a device driver type operation. We'll mention that later. And then, of course, you have things like divide by zero exceptions, and those go into the kernel, and typically you just kill off the process at that point because they did something really bad. Okay? And so does anybody know how many modes, so that we need at least two, how many modes does x86 have? Do they have two? Yeah, 4. So the x86 processor actually has 4 modes. And typically what happens is you use mode 0 as kind of kernel and mode 3 as user mode, and the other two are often not used unless you do some interesting things with virtualization. But those 4 modes are sort of part of the military spec for security. You can ask me about that another time too if you want. The other thing we talked about, just briefly reminding you, was we talked about this idea of simple address translation as part of our protection. And here, what we see is we've got a base and bound register, which we add to the register state. Program addresses actually go through a translation process where in this simplistic version, we just add the address to the base, and that gives us the new physical address, which is where this data actually lives in physical memory. And what's great about the base and bound here is now that when we're in user mode, any attempt to go below the base or above the base is prevented, and as a result, we've protected the kernel and other processes from the yellow process. Okay, and obviously, you can think about this. How does dual mode operation come into play? It comes into play in that when you're in user mode, you're not allowed to go outside of base and bound, but also you're not allowed to modify base and bound, right? You can imagine that if you could modify base and bound, there's no point to this. Kernel mode, on the other hand, typically it ignores base and bound, and you're free to modify the base and bound registers. Okay. And then we threw this out really quickly. This is a schematic view of what actually happens in a lot of real processors today, where there's a translation table that takes segments that are made up of a bunch of pages, sends them through translation, and that translates to the physical portions in the memory, and different processors end up pointing at different parts of that space, and we'll talk a lot more about this as we go on. But once again, dual mode translates to only the kernel can alter the translation tables, which are these bubbles. Once you're in user mode and running the blue process, you're basically stuck to the translation and you can't do anything with it. And as a result, blue can't mess with green and green can't mess with blue. The kernel can, of course, screw them all up, but that's the kernel's in charge. Okay? We good? All right. And I just threw the word page out here and a couple other things, so they'll be rattling around in your brain for when we finally get around to really talking about this stuff. Okay, so here was kind of putting everything together. So notice that we have kind of user mode at the top and kernel mode in the bottom. And here's for a web server. What often happens is the web server actually does a system call read, which goes into the kernel. And that read says, I'd like to read the next request off of the wire. And if there aren't any requests, the kernel will actually put that process to sleep and let something else run. Sometime later, a packet comes in off the network, causes an interrupt. That interrupt ends up taking the sleeping process, puts it back on a run queue. We do a return from user at some point, and now the process is running again. And at that point, it maybe says, oh, I got to read something from the disk, and so it puts a read into the queue. That read has to go to sleep because we got to read off the disk. The disk device driver actually starts the disk operating. Sometime later, there's an interrupt because the disk read is done. That causes a return from interrupt, and this process gets to run again, at which point it puts the data back out on the network. So you can kind of see how these different crossings of the user to kernel mode happen, and also you can sort of see how processes like the server process interacts with other things that are happening down in the operating system, like, for instance, it gets put to sleep while waiting for an interrupt from the network, or it gets put to sleep while waiting for an interrupt from the device driver that has the disk attached to it. Or the disk that has the disk's device driver would be a better way to put that. Okay? Good. So you guys we're starting to put all these things together. Were there any questions on that? Okay. So, suppose we want to run many things at once, and we sort of have all the basic mechanisms now that we put together. So we can switch between user processes and the kernel. The kernel can switch among user processes by deciding when it puts one to sleep, what to do with the next one. We talked about that. We've talked about how to protect the operating system from user processes and how to protect processes from each other. All of those things were the last lecture and a little bit of this lecture. Notice that the primary protection mechanism that we've been talking about so far has been the address translation mechanism. We prevent one process from touching the memory of the other one. That's been the primary mechanism. There's been a lot of subtle ones underneath the covers, though, however, like processes are not allowed to mess with the disk drive or not allowed to change interrupts and turn them off. There's a lot of other subtle things there that you can imagine that if a process could mess with the interrupts or mess with the devices, that would kind of screw up other processes as well. Okay? So what are some questions we might have? So we might ask things like, well, how do we represent a user process in the operating system? How do we decide which process to run? How do we pack up the process and set it aside? How do we get a stack and heap for the kernel? For instance, we've been talking about stacks and heaps for processes, but we haven't talked about the kernel. And we might even ask the question of, aren't we wasting a lot of memory with all of these little structures for different processes? That last one, the answer is pretty much no, because memory is pretty free these days. But let's talk about a couple of the other ones. So there is, not surprisingly, something we call a process control block in the kernel. Every operating system represents process control blocks a little differently, but it's a structure, one per process, that essentially says what's the status of the process, what's its register state. So that means when I put the process to sleep to run somebody else, I save all the registers. I save the program counter. All of that stuff has got to go somewhere. It goes in the process control block. Things like the process ID. What user started it? What's the executable code? What's its priority? How long has it been executing? What's its memory space, etc.? All of that stuff gets stored in the process control block. This is the identity of the process, and when you put it to sleep, it's all of the state of the process required to start things up again. All right? And the kernel scheduler, which I'm going to briefly talk about in a moment, and which we're going to talk a lot about in a few weeks, basically maintains a data structure of all of the process control blocks and decides which one to put on the run queue every now and then, right? Oh, I'm going to take this one off, put that one on. That's what the scheduler does. It schedules. Okay, don't you love it when terms actually mean what they mean? And the scheduling algorithm selects which is the next one to run when you take something off. And the scheduling algorithms are actually quite interesting and complicated. So here's a schematic of the scheduler. It's a very complicated thing, right? If there's somebody who's ready to run, select one. Run him. Okay? Otherwise, if there's nothing ready to run the idle process. Okay, so most operating systems have an idle process, which is the thing that runs when nothing else needs to. And that idle process typically tries to put the processor in a low power state so you're not wasting power and so on. Okay, but this loop, as silly and simple as it is extremely sophisticated. Why? Because of this select process. That's the scheduler. Given a list of things to run, what do we do next? Well, it's in there, and that's where we get all sorts of interesting stuff. So scheduling is basically the mechanism for deciding which things run, and lots of different scheduling policies. Fairness, or real-time guarantees, or latency optimization, or you pick it. There's a scheduling algorithm for it, and we're going to talk about several of them a little later in the term. In fact, you're going to get to you're going to get to implement the scheduler in Lab 2, so you get to play with scheduling as well. I love that enthusiasm there. Okay. So how do we safely let the user hand over a task to the kernel? You could imagine that if we let user code jump into the kernel anywhere with kernel privileges, we're probably in trouble. It's kind of like, again, you're at a concert and there's the bouncers at the door. You're trying to go in somewhere. If you had some secret way around the bouncer, then all of his access list or all of his controls that he's supposed to be putting on that concert or that party or whatever are violated, right? Because he's never actually checking you. So we have to make sure that when we allow transfer into the kernel, we do so in a very controlled way. And among other things, we have to have very controlled tables, and I'll say a tiny bit about that, and the stack is going to be different, because who knows whether the user has screwed up their stack or not. Okay? And so carefully constructed kernel code typically packs up the user state, sets it aside, sets everything up cleanly for it to run, itself to run, and then it runs. Trust nothing. Okay? And the kernel is very paranoid when it comes to letting user processes do stuff, because that's important. And it should be impossible for a buggy or malicious user program to cause the kernel to do something and corrupt itself. That ought to be sort of our goal from a security goal. Many of the interesting security violations that hit the headlines are all about or often represent cases where somebody's found out a bug in the kernel's entry mechanism that allowed them to get around the controls that are in there, and as a result make an uncontrolled entry into the kernel with privileges such as kernel mode, and once you've done that, then all bets are off. Okay, anybody here taken 161 or any of the security classes? A few of you? Not yet? Good class. They do talk about things like buffer overrun errors and so on, where you actually can trick a kernel into running code that you've loaded onto its stack. Those are pretty bad. So one of the things that I wanted to bring out in this sort of idea is the need for kernel stack. And so basically you're not allowed to put anything on the user stack when you're in the kernel. And there's at least 2 or 3 good reasons for this. The first one being, well, the user might have screwed up their stack pointer, and so if the kernel goes along and blithely tries to use the stack pointer, there might not be a stack. Okay, you got to start thinking like a malicious user when you're trying to design your kernel, right? The other thing is, it could be that the user stack is not big enough. There's lots of things that could be wrong with the user stack. A subtle one, which you probably haven't even considered, is if you have a process with 2 threads, remember we decided the process is the container, the threads are in the process. If you've got a process with 2 threads and one thread enters the kernel, there's nothing to say that the other thread can't look at the stack of the first thread. Why? Because they're in the same address space. And as a result, if the kernel is putting sort of private information on the user stack as in response to entering the kernel, the other thread can see that. So lots of good reasons for this, but the bottom line, which is a simple thing for you to remember out all of this, is that every process typically has both a user and a kernel stack. And the user stack is used when you're in your user mode, and the kernel stack is used when you're in kernel mode. And you can see kind of three instances here. Here's one where we have a running process, and it's running at user mode, and so it's using its stack up and down, and the kernel stack is just sitting there. Here's another one where it's in the scheduler ready to run, but not yet running, and typically there's some user state that's on the kernel stack. Okay, and then here's one where we've actually done a file read or write, and we're waiting for I/O. And so what you can see here on the call chain, if you can track this with me, is you start with main and you do a couple of procedures, and then you hit the system call that says read. That jumps into the kernel. The kernel grabs its stack and saves the state, and then we start entering the system call handler, and we go to the top level of the device driver, which I'll say in a little bit. And what happens? We start reading from the disk, which could take a long time, milliseconds, and so we just go to sleep. And so this would be what the two stacks for that process that I showed you from the web server earlier looks like, where it was doing a read, and it went all the way down to where it asked for something off the disk, and then it got put to sleep. Okay? So, questions? All right. So, this is just a very simple example with x86. So we have, here we're running at user level, we're running some code, so the code segment's pointing at the code, the stack segment's pointing at the stack, and during the interrupt we actually switch over where we first save all of the user's stuff on the exception stack inside the kernel, and then we point at the kernel handler and we start running from there. Okay. Questions? So, let's talk about system calls for a moment. And it is interesting, I think, that we haven't actually seen any system. How many people have seen a system call in the code you've written for Homework 0? Uh-huh. Not surprising. We'll talk about that in a second. But how do we handle these elusive system calls, right? What actually happens? So they vector through well-defined entry points, and that's, again, the bouncer is the best way to think of this. The kernel's got a bouncer who handles system calls. All right? And it's a table mapping the system call number to the handler. You locate the arguments that the user decided to put into that call, and there might be in registers and they might be in the stack. You copy those arguments into kernel memory. Okay, why do you do that? To protect the kernel from malicious code, evading checks, and protect the kernel from the user saying it's got access to memory, it doesn't. There's lots of reasons for doing that. And then you validate the arguments to make sure that they're not crazy. You know, did they ask to read -1 bytes from a disk drive? Okay, that's probably bad. Right? And then, when you're done, you copy the results back to user memory. You can't give the user access to kernel memory. And that's a little bit of a lie, and maybe we'll talk about zero-copy optimizations later in the term, but for now, let's take this as it is. And as you can see, it's all about making sure the user can't mess up the kernel. Okay? All right. Questions? Now, let's talk a little bit more about what we need for hardware support. So I had a couple of questions about interrupts last time. But so interrupt processing is not really visible to the user. It's something that occurs between instructions. And it's something that's basically it happens. You get restarted transparently afterwards. And the user code never knows the difference. Okay, and why is that? Well, that's because the code that's running probably has nothing to do with the interrupt. The interrupt is for a disk read from some other process. Okay, and so we want to make sure that when the interrupt happens and finishes, that it doesn't mess up the running process. And here's an interesting question here. Suppose we arrange the process is running, an interrupt comes in, we handle it, the interrupt goes out, we start the process back again. What could that process actually observe with respect to interrupt timing? Even if we're extraordinarily careful That the interrupt comes in, it's processed, it goes out, and we restore all the states so the user doesn't know that the interrupt came. What could we still observe? Yeah. Yeah, what about time? Okay, I'll buy it. Time. What about time? Yeah. Yeah, so maybe the clock is still running, and so we don't have perfect virtualization because we can notice the time has happened. Does that tell us anything? Maybe. So it turns out there's a bunch of ways of observing what are called side channels, and I don't know if they talk about this in 161 or not, but oftentimes you can get information out of timing. So you didn't actually get to see the data, but the fact that the interrupts were coming at a certain interval or whatever might tell you something about the data that was being transferred. So anyway, the interrupt handler gets invoked with interrupts off and re-enabled on completion. Okay, so this is non-blocking. We always run to completion. We pack things up and finish it. We'll talk more about interrupts later. But for instance, during interrupt processing, the kernel may actually enable or disable interrupts by itself. The user is never allowed to enable or disable interrupts. Why is that? Yeah. You what? Yeah, if you disable interrupts, you could turn off the timer and get to run forever. Yeah, what else could you do if you disable interrupts? What was that? You could lose data. Why? Because data comes in off the network, the interrupt doesn't happen, another packet overwrites it. Yep. You could lock the system up so that no Control-C or anything could get you out. There's lots of reasons why users should never be able to touch interrupts. So if you think about all the times that you trust your operating system to come back to you, even when bad code is running, they clearly get screwed up if you're allowed to disable interrupts at user level. And the hardware may actually have multiple levels of interrupt, which I don't want to say anything about right now, but I did want to show you an interrupt controller so that interrupts aren't entirely mysterious. So oftentimes inside of one of your computers is a piece of hardware called the interrupt controller. And the idea here is that each of your devices are connected to an interrupt line, and when the device needs to get computer service, it will raise the interrupt line. And that interrupt line goes through the interrupt controller, and if all is enabled, will actually tell the CPU to go ahead and interrupt. And notice that one of the things I've shown here is that there's an interrupt mask typically, so often the operating system, when it's processing certain types of interrupts, will actually mask them off so that additional ones won't occur. Or maybe it's processing a disk request and it doesn't want to get network requests, and so it'll mask off the network requests. So the operating system can turn on the mask to turn things off. Okay? Notice what I've got here, by the way, is that as soon as an interrupt occurs on a lot of CPUs, what happens immediately is that all interrupts are disabled long enough for the operating system to decide what it needs to do in terms of enabling or disabling specific interrupts, and then it's up to the operating system to re-enable before the interrupts occur again. Okay? The last thing that is a good thing to know about is what's called a non-maskable interrupt. What's a non-maskable interrupt? An interrupt that can't be masked. Okay, good. All right, I know you guys are with me. So, what would be a good type of non-maskable interrupt? What's an example? Anybody? Well, an exception, though, isn't really an interrupt. An exception is something that happens because the program tries to do something like divide by zero, and that takes you into the kernel. That's not an interrupt. Interrupts are things from outside. They're asynchronous. What's an, yeah? Could be if you hold down your power button. Yep, what else? Yeah. Well, but see, network packets, you've got to be able to disable interrupts while you're processing a given packet. So, keyboard, again, you might want to be able to disable a keyboard while you're doing something. Yeah. Yeah, writing to memory, you probably want to keep going too. Yeah. Yeah, okay, so you guys are actually all giving me things that the operating system wants control over. A good example of a non-maskable interrupt is something like a memory fault where the memory just got a non-correctable error and there's really nothing that the operating system could do about it. You might get a non-maskable interrupt. Or power failure. You've only got a few milliseconds worth of compute time because the power just went out. This is an interrupt. You better do something now. Okay, those are examples of non-maskables. Okay, so how do we take interrupts safely? So just like with the system call case, we have an interrupt vector. I showed you that last time, where each device goes to a specific handler. We have a kernel interrupt stack, just like we had a stack associated with processes. This is associated with interrupts. We have the ability to turn off interrupts so we don't get stuck in recursive interrupt loops. And we basically have, when an interrupt actually occurs, the hardware goes ahead and atomically saves things like the program counter and the stack pointer and a few things before it ever transfers into the kernel. Okay, good. So, questions? So these are all controlled entrance into the kernel, okay? And I wanted to make sure that you guys had all seen that at least once. So let's talk about a little administrivia. So my office hours, it looks like they're going to be 1 to 2 for now, Monday and Wednesday. If that ends up being a really big problem, we'll do something about it. But those are my initial ones, and my office is in Soda Hall, so we'll see how that goes in terms of the size of this class. I may have to hold them elsewhere, but homework 0, you should be working on immediately, but it's due on Monday instead of Friday. Gave you a little breather. Okay. Thank you. Yes, I do Thursday nights also the couple of reasons for this, one was we thought we'd give you a little bit of a break. The other is that I know that there was some confusion about some of the things in the homework, and so we thought we'd correct that. But mostly it's because I think we're going to make homeworks due on Mondays, and so we thought we'd normalize on our homeworks. But okay, you should really get going on this, by the way, though, because it's sort of everything you need to get the class going. And you should be going to section already. So you hopefully went last section. Hopefully you'll go this section Thursday and Friday. We're actually noticing that for some crazy reason, even though we have a Friday 10 to 11, 2 Friday 10 to 11 sections, that they're underattended. I don't know why that would be, but we're kind of thinking we might try to have another Thursday section like 12 to 1. Would that be useful to people? No promises there. I'm going to see if I can figure out how to do that. But there is a disadvantage, by the way, if you're in a really large section, and you should consider finding smaller ones, which is there is a participation aspect of this grade, and the important part about that is you want your TAs, ATA, to know you well, so that you're in the, you're asking questions in class, and you probably want me to know me well as well, so that's why it's good for you to come to class. But this is a pretty good reason to find smaller sections because you're more likely to get good question answers going on, and you get a TA who knows you better. So that's a thought for redistributing. Also, Friday, is the drop date for this class. This is an early drop class. It's shown, that's actually in the course book, and there's not much more to say about that. It's sort of, you better make a decision about the class and drop on Friday. I would say the following. If you're actually thinking that you're going to drop, it'd be better to drop a little earlier than Friday so that people who are still on the wait list can get in. Okay? And pretty much the wait list will be resolved by Monday. So as of right now, things are looking reasonably good in that I think Michael David told me there were only somewhere between 4 and 10 people on the list, depending on how you count. So we're getting down there if you're on the wait list. But if you're thinking you're going to drop, I'd say try dropping sooner rather than later. And that's not that I'm wanting to get rid of anybody, just saying that if you're going to drop anyway, give people the option to come into the class. Once we have the class membership figured out, then we have group sign up, which will be out next week. And again, we want to have 4 people in a group. So hopefully you've been looking for your partners, and we'll make it very obvious how to do that. We'll have the form out and everything. Are there any questions about this? No? Okay. Finals conflicts. So I've had a couple people tell me that they're trying to take a class that overlaps this one. And as a result, there's a finals conflict, and can they move the final? No. So we're not going to help people take classes that you cannot attend one or the other of them. So, and this is a pretty large class compared to EE 122. Now, if you can convince the EE 122 professor to move your final for you, okay. But I would suggest not taking 2 classes that overlap in actual hours. Other than that, if you have a really good reason or good conflict for finals, let us know earlier rather than later, because we're going to have to figure out what to do about it. Okay? So we need to, but if you have a conflict, you have to give us a good reason, which, like I said, doesn't include EE 122. Any other questions? By the way, the scheduling office does occasionally screw up and have overlapping finals for courses that aren't overlapping, and those we clearly will help you with, obviously. Wow, okay. Got through the administrivia with no problems. I know we have at least one section that's got 40 people in it. If you're in that section, it might be good to try some of the other ones, because 40 is a lot. You know, I guess if you want to sort of sit back and hear what everybody asks for questions, that might be one reason to go to a really large section, but that seems like that's one of the few. So I'm getting a thumbs up on trying to get a Thursday like 12 to 1 section. How many people would attend that if I had it? Just a couple of you? Raise your hands up high to see whether it's worth the trouble. All right. Okay, that might be something. Okay. All right. So processes are instances of programs executing. This is what OSs do. And processes do their work by processing and calling file system operations. So the first question we might ask, processes are the active entities we've been talking about this whole time. The question really is, are there any operations that you want to do on processes themselves? So not, processes doing things, but what might you want to do with processes? Anybody? Yeah. Make new ones. What else? Yes. Kill old ones. What else? Yeah.
I might want to read the virtual memory so I can hack the game that I'm reading and something.
You want to hack processes. Okay, we're not going to necessarily help you do that early on in the class at least, but okay, yes. You might want to suspend it. What else? Yeah. Yeah, you might want to share stuff. So there's actually a lot of operations on processes that external parties want to do. And so, one of them obviously is exiting, and so on. But so in order to look at sort of what operations you might want to do, let's start thinking about what a process is again. And here's a bit of code that you could imagine using where we actually call get PID to get an integer, a special PID-_T type, which is actually an integer. And then we print out the PID and wait until a character is pressed and then exit. What is this program doing? Well, you could read the notes here. Get, current, processes, PID. So when you do PS AUX or PS whatever, how many people have executed PS on a Linux-style system? Many of you. You get back a list of the running processes and all their PIDs. That PID is a unique identifier that's used both in the shell, that's homework number 1, and by other parts of the operating system to refer to processes and thereby do operations on them. Okay? Now, can a process create a process? Certainly. How do you do that? Yes? Sure. Previous slide. Go for it.
What's happening at the bottom when you do the get character from standard in?
So this is actually waiting until you press a character, at which point it exits. So this thing is prints the PID and kind of waits until you press a key, and then, good question. Yes? Same thing. So yeah, you can just return out of this, return a 0, you kind of do the same thing. But exit is a nice way to make sure that you sort of make it clear what the return code is. So, can you create other processes? Certainly. There's a system call called fork, which you're going to become very familiar with over time. And what it does is it creates a copy of a process. All right? So, what do I mean by a copy? What I mean is you take a given process, it executes fork, you construct a complete copy of that process. All of its memory, all of its file descriptors, we'll say more about that in a moment, all of its state becomes copied into the new process, and now you have 2 of them. Okay, it's kind of like a cloning operation. Okay, what was that? The ID has to be different. Okay, so the one thing that's different is certainly the ID is a little different. And actually, the fork system call, I'll show you some code in a moment, has a return value from it. And what's interesting about this is the value that comes back from fork is either greater than 0, in which case you're running in the parent, and that new ID is the new PID of the new child. Or when it's 0, you're actually running in the new child process. And if it's less than 0, then there's an error. So fork is a really funny call. You call fork, and it returns twice. Once in the original process and once in the child. Okay, by the way, we call the resulting new process a child. Okay? So, all of the state of the original process is duplicated. Memory, file descriptors, everything. Okay? So here's an example of some code. Can you read that? Okay? That little red thing is an example of calling the fork system call. Actually, you're calling a library call fork. You get back this child PID. If the child PID is greater than 0, then you know you're in the child. And if it's 0, you're in the parent. Excuse me, let me say that again. If it's greater than 0, you're in the parent. That's what I meant to say. If it's 0, you're in the child. Otherwise, you've got an error. Okay, and now, by the way, this is a very standard thing in Unix-style operating systems, that whenever you get a return value that's less than 0, there's an error here. So keep that in mind and get used to looking for that. Okay, it's almost always the case that -1 or -2 or negative something is actually an error. But for now, the key things here are these 2 pieces we see here, whereas if the return value is greater than 0, then we are the parent and we've been told what the ID of our new child is. And if it is 0, then we're the child and we're not helped with anything, and we actually have to call get PID to find out what our PID is. Okay. Now I'm going to show you this code in a little bit larger instance in a moment, but are there any questions? Yeah.
Does the kernel have to know when you create a new process?
Yes, because the kernel is fundamentally involved in making a new process. Because it's got to set up a new address space. It's got to copy everything from the original parent to the child. It's got to allocate a new ID and a new process control block and so on. So the kernel is fundamentally the thing that creates new processes. Good question. Yeah?
I have like 2 questions.
Okay, you can have 2 questions.
First one is, so the parent process execute first.
Ah.
The child process finish executing. The parent wants to delete.
So that's a really good question. Does the parent run first and then the child? Is that what you're asking?
Yeah, and like kind of like if one does the child have to finish before the parent or whatever.
So no to both questions. The parent and the child run in parallel. Okay, and remember what we said earlier in the lecture and last lecture where we sort of, how do we get in parallel? Well, maybe we multiplex things. So once you create a child, now both the parent and the child are both exchanging time on the scheduler queue and the run queue, and they're running in parallel. And so you don't have to wait for one or the other to finish before the other one executes. Now, there are special calls because you can imagine the parent would really like to know if it sends a child off to do something, it'd like to know when the child is done and has exited, and there's a special system call for that called wait, which I'll show you in a second. Okay, that was question number 1.
Is the child process also known as accept process?
Sure, you could call that a sub process. What was that? Oh yeah, the question was, is a child process also known as a sub process? I will say yes. I haven't heard that as frequently, but sure, I believe that could be true. Yes. Question? Does killing the parent process kill the child? That's, I don't know whether to answer. No. No. Okay, typically what happens is so what I'm not showing you here, and we will talk about, I think, later, is there is the big tree. There's the root parent called a nit, typically in a lot of operating systems, and then everything's a child after that, and you can imagine a tree of parents and children and so on. And when the parent dies before the child, oftentimes the child gets inherited by a grandparent. Okay, so just like in, I guess, in real life. So, okay, other question. Yeah.
I have 2 questions. So my first question.
2 questions. Number 1.
The child process doesn't necessarily have to be a copy of the parent process, right?
Okay. So there doesn't necessarily have to be and is. So in most Unix variants where you execute fork, the normal fork, it's a complete copy. However, it turns out Linux, if you go there and go deep inside, fork is actually implemented with something called clone, where it's not required to actually have things be a complete copy. Because you're obviously going somewhere where you're saying, well, I'm making a child process, but I'm going to do something different with it. Okay, and actually what I'm going to show you in this lecture in a few slides is we actually call exec to start something new inside the child rather than what the parent had. And at that point, we actually throw everything out and start something new. So for your current understanding of fork, it seems very wasteful because you make a complete copy, you throw everything out, you run something different in the child. Okay, but keep that as your mental model of fork for now. Second question.
Does the parent-child relationship come with any special...
Strings attached? Always. So parent processes are able to control children processes directly. Oftentimes, they can wait for the child process to exit. It's a lot easier for the parent to manipulate the child. Didn't realize this is going to be a parenting lecture today. Okay. Yes. Sorry, could you speak up? Sorry, go ahead.
Between the fork call and any manipulation done with CPID, is there any way for something to go wrong, like killing the child process and getting reused or
That's an interesting question. So you're saying between when this fork call executes and we actually check the CPID, could the child process get killed and that get reallocated? Is that what you're asking? So no. And the reason that typically doesn't happen the way you're worried about is that the actual process control block, that's a very good question, by the way, is not reallocated until the parent executes a wait on it to find out what its return call was. So what actually happens is if you create a child process and then it dies right away before the parent does anything with it, it actually stays in a state called the zombie state. Okay? So yes, we can have zombie children as well running around. Okay? But you're not going to reallocate the process ID until after that parent sort of gets a return call from it. And when that screws up, by the way, the communication between the parent and the child gets messed up for some reason, then what happens is at that point you actually got a bug and you'll see a lot of zombie processes that can happen. So, okay. Any question? Go for it. So the state, think of fork dives into the kernel in the parent. So the parent calls fork, and at that point we're in the kernel and the parent is suspended. They're not running. And the kernel goes ahead and does its copy operation, and we don't return back to the parent to do something different until after the copy is completed. So the funny thing about this is both the parent and the child start from the instruction after fork. Right? So suddenly you called fork in the parent, but now both the child and the parent return from fork. Dun, 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 which is kind of weird, right? And we can do that because we've copied everything. And so the fact that the child and the parent both return from fork, and with the only difference being the value returned from fork, everything is in the same state, so all of the local variables are the same and everything, so we can actually do that split and come back from both the parent and the child, both returned from fork. Okay? Good. Now, of course, I've just sort of shown you the key kind of parentage of most operating systems. When you see lots of processes that are running, they all have parents, and the parents have parents until you work your way up to something often called a init. And then init is the first process, and it calls children, and so on, and that's how you get all the processes. All right? And shells, which are things that you type commands at, and which you've started to have some experience with in Homework 0, and which you're going to have more as we go on, actually are programs whose job it is to create and manipulate processes for you. So a lot of the running processes end up being children of a shell, just because that's kind of the way it worked, right? All right, good. So process management, simplest form of this is fork, which is a system call to create a copy of the current process. It has no arguments. Exec is another interesting call, which is it changes the program being run to something else. Okay, so oftentimes what happens is, let's talk about the shell. You fork a child, and then that child immediately calls exec and loads a new program into its memory address space. And that's exactly how we start up a parallel program running. We start with a copy through fork, and then we load through exec a new child process, or a new program. Okay? Wait is a system call that basically lets a process wait for its children to finish. Okay? And you guys should do a man on wait to see there's lots of different variants of it. But it's a way for the parent to get that return call coming back from exec, from exit. Boy, having a hard time today. So when you say exit 0, how did that get reflected to the parent? The parent executed a wait and found out what that return value was, which, by the way, at that point releases the process from being a zombie, the child process. Okay? And then signal is a way for processes, not necessarily children or, basically any process can signal any other process. And a signal is like a user-level interrupt. So when you control C on a program that you tried to run that's, computing the last digit of pi and you realize you already knew it was 5 from last time, what you do with that control C, I'm still kidding, is it sends a signal to that process saying, hang up. It's a hang up signal, go ahead, stop. All right? And that's a signal. Okay? And that interrupt handler exits. You can change the interrupt handler in a process that you construct so that when it receives the control C signal, it ignores it and returns back to where it started from. What's that going to cause? Can change the signal handler so that the control C signal is ignored and you return back to where you were executing when you receive that signal. What does that process behave like? Yes? Huh? Well, yeah. So what's the basic behavior? Suppose you start executing a loop in that process after you've changed the signal handler. What happens? You can't kill it because the way that Control C works is it sends a signal, and you've told that signal to be ignored, and therefore you've just made an unstoppable process. Now, unstoppable is really not true because there are some signals that you can't do that with, and so the operating system can always get control. For those of you that were excited by that all of a sudden. So I wanted to just throw this code up once again. This is a blow-up of what we saw previously. So notice, and a little bit different, so notice that we execute fork. We notice that we're the parent process because CPID is greater than 0. We get our own PID, and here we're saying, oh, look, the such and so is the parent of such and so, and I sort of say what my PID is and what my child's PID is, and then I execute wait. And that wait system call actually waits for the child to finish. Okay, and then when I'm done, I can actually say what the result was. And look down here, here's the child process. The child process gets its own PID, executes what its PID is, and then it exits, and when we're done, then the parent gets to wake up from wait. Yes?
Does a parent process always only have one child, or can it have multiple?
Parent processes can have many children.
If that's the case, then how does it know which one's waiting for when you call wait?
What you get back is the ID of the one that you got wait from.
So you don't get to pick when you call wait, you just have to see which one.
That's right. Typically, you have to see which one it was that has exited. Okay. Questions? All right, good. So finally, to finish this up, so here's a typical situation where we fork to get a new process, and if the PID is 0, which means it's the child, we immediately execute exec, and that gives us a brand new process that's completely different, and so on, and this is how we get all the different programs running in the system. And then eventually the parent can execute wait, and it'll wait for this particular exec program to finish. And so this is exactly what a shell does. It executes fork, it execs something brand new, and as a result, this is a brand new program, and when that program exits, then the child or the parent wakes up and we're done. Okay? So this is exactly what happens when you execute a command on a shell. Yes? Yeah, so typically when you put an ampersand in there to put it in the background, then you're not executing wait, you go on and do other stuff, it runs in parallel. And then if you don't, and then oftentimes it exits and somebody else is watching trying to execute wait so that when that process exits, it doesn't go into a zombie state. Because you've sort of said, I don't care about the return value at that point. Good. All right, and what's the shell? A shell is basically a job control system. It allows the programmer to create and manage tasks. Good example is, you type this at a shell, compile, link, run. How many people have done that sort of thing recently? A few of you? Okay. All right. Next time, you're going to get to play with the shell quite a bit more for homework number 1. So finally, I wanted to show you signals. As I said, this was like an interrupt handler. Notice, this is, we start at the main entry point of the program, and at this point we say signal. We say which signal we're interested in, and we give it a handler. And so this has just changed the natural sig interrupt handler to this signal callback handler, and as a result, and then we go and we do something like an infinite loop that's computing pi. And now when we hit Control-C, rather than this immediately killing the program, it actually calls our own handler, at which point we sort of say, oh, caught signal, whatever, and then exit. So what we've done here is we've actually changed the native signal processing of this particular task. And this gets to be very useful when you're trying to design a program that interacts with a user and you don't want them to Control-C out. You want to trap all the signals yourself and do something more intelligent than just dying. Okay? Good. Last but not least, so somebody tell me about this. So here's the code. What does this program print? Now notice, by the way, these sleeps are commented out. These 2 bars here give it a comment out. So, anybody want to hazard a guess? So notice that what are we doing up here? So the parent basically says what over and over again? Parent, and gives a number, parent gives a number, parent gives a number. This one, child gives a number, child gives a number, child gives a number, and notice that those numbers are what's happening. Here we're incrementing them, and here we're decrementing them. Yeah. So yeah, so both of them have the same standard out. So anything we see is going to be interleaved in the same grouping. Good question. What else? This I, notice this I variable seems like it's shared, doesn't it? Doesn't it look to you like the parent is busy incrementing and the child is busy decrementing? So they both start at 0 and the parent tries to increment up to 100 and the child tries to decrement down to minus 100. Does everybody see that? Do those two things interfere with each other? Okay, who thinks no? Okay, who thinks yes? Okay, the guys, good. No. Why? Yes. Yes, they're completely different processes. The I's here started out being the exact same thing, but by the time we split them into two processes, they're different I's. So the parent goes up, the child goes down, and we're good to go. Okay? Good. So let's take a brief break. Let's take about 3 minutes. Stand up, stretch, say hello to your neighbor. Contemplate infinity for a very short period of time. I'll leave this other code up here for you guys just to contemplate it if you're still wondering about it. All right. I heard a sudden lull. Everybody wanted to learn all of a sudden. So, here's a question that I didn't ask you. Suppose I put one of those sleeps back. What happens? Does the result change? Yes. Okay, so the ordering of the prints will change, right? Because they're both printing on they're all doing the same thing, but they're shoving all their print statements into the same screen. Okay, and so by putting sleeps in there, we'll change the timing. And in fact, if we put enough sleeps, if we put sleep 100 or something, it's possible that one of them will completely finish before the other one starts. Or before before the other one gets to the second one or whatever, but second loop. But anyway, nothing to do with whether the parent prints all the positive numbers and the child prints all the negative ones. That's going to stay the same and is unchanged by sleep. Okay? Now, I wanted to recall again this brief picture I put up last time of a typical Unix system structure with user mode, kernel mode, and we've been talking about this the whole time where they have applications up here, including these processes that are running fork, and then we've got a whole bunch of kernel code, and the thing we've been talking about is kind of transitions to user mode and kernel mode, and I want to push on that a little more. So how does the kernel actually provide services? And of course, services are things like file systems or printing to the screen or whatever. And, I keep saying syscall, but you've never seen a syscall. Why has you as a programmer at user level never seen a syscall? Yes. Yes. Syscalls are embedded in libraries. You've been using libraries. In fact, the fork that you saw earlier is really a library call to a procedure that calls a fork system call. Okay? So, we've been writing all sorts of useful applications. You have too. You've never seen syscall. And that's true. It's buried in the runtime library. Okay, like the C library is a good example. Okay, when you link, there's a whole bunch of things. We just saw an fprintf earlier. There's a bunch of functions. Those are the things that have the syscalls inside of them. All right? So, and so basically, if you kind of look at our picture here with lots of processes running the OS, you could think of all of these have different functions. Green is doing one thing, yellow is doing another. They all have the OS library. Green application calls functions that are in the C library, and the C library makes system calls to the operating system. And so it's often the case even that a single request from the user program to a library ends up making several system calls. Okay, it's possible. Because the system calls are the interface between user and kernel mode, which isn't necessarily the interface you want to give a programmer. It's a security interface, right? It's that interface of protection between user mode and kernel mode. Sometimes it's a convenience interface for things like file systems, which we'll get a bit to today. But by and large, you can make anything out of the system calls and turn them into much more useful things for users to use, and that's the way people usually use system calls, is with libraries. Now, so this is kind of, if you've taken a networking class, you sort of often see the narrow waist, where the narrow waist in the middle there is IP. Here, it's the system call interface, and across many different flavors of Unix, for instance, the system calls are roughly similar, except, and so basically below it, you've got different implementations of the kernel, and above it, you have libraries and different applications, and the whole idea of an application being portable to Linux and Mac and a bunch of different Mac OS and a bunch of different OSs is really hinging on the notion that the system calls are similar enough that it's really easy to port them. Now, Linux, does anybody know, how did Linux handle the portability thing? They just included every system call of all the different operating systems anybody could want. So the Linux system call interface tends to be a little bit less well thought out. Okay? But anyway, nonetheless. So basically, one of the things we can talk clearly requires going across this interface is processes, and we've talked about those. But now let's talk a little bit about I/O. So some key ideas of I/O is we're going to pick that interface going across that narrow waist of system calls so that it's uniform despite the type of device. It could be a disk drive. It could be a remote cloud storage service. It could be a little USB key. All of them are going to be vastly different devices, but through that little system call interface, they're going to be the same. And by making things the same across that system call interface, it makes it really easy for programmers to interact with a variety of different storage devices without having to care about how to do that. Okay, disk drives, you may have to worry about seeking and optimizations based on whether the head's moving around a lot. In a USB key, you don't have to worry about that. With cloud storage, you might have to interact with some other things. But by having the same interface, basically the program is just reading and writing data. All right, and so basically, as a result, we can do some very simple composition, put find, feeding into grep, feeding into word count, da-da-dump, and this uniformity doesn't matter, doesn't change based on the device type. And you're going to get a lot more of this as we go on, but the basic idea behind this uniform interface is you open a device, and then you use it. Okay? And this was actually a pretty radical thing. In the graduate operating systems class, we always read one of the early BSD Unix papers where they sort of present this idea, well, we're going to open, read, and write to a disk drive in exactly the same way as a keyboard and in exactly the same way, and we're going to just present the same interface to everybody. Okay? And that has been a Unix philosophy for 30 years now, but it was new when that was presented, and it's a very easy way to interact with devices. They're all the same at some level. Okay? And it's byte-oriented typically, so we're reading bytes. So even if the disk drive transfers blocks of data from the device into the kernel, the interface that you often use to it is byte-oriented. I read a few bytes. Okay, does anybody know what the typical block size coming off of a disk drive is? Okay, I see an optimistic person saying 4K. Those are the very new drives. That's correct. 512 bytes was another one that was pretty common. So every time you read something off the disk drive, you get a big chunk of stuff, but the user program is reading and writing bytes, and they don't care because the interface is common. Okay, and we'll talk a lot more about this as we go. But the kernel buffers the reads up and gives you a streaming interface, so you get a stream of bytes no matter what you've got. And the other thing to note, by the way, is that when you go to read and that the data's not ready yet, well, the disk drive has to move its disk head into track 23 to get your data. That's a long-running operation. How long does it take to seek to a track on a modern disk? Okay, and now for those of you that are a little lost on this, imagine a modern disk is a spinning piece of magnetic media, and we have a little head that moves in and out to get the data off of the disk. And we have to move the head in and then wait until our data goes under the head, and then when the disk rotates enough, we read it off the disk and put it in memory. Okay? How long does that typically take? Yeah. Okay, that's a little low, but that's good. Order milliseconds, yes. 3 to 7 milliseconds, 8 milliseconds, somewhere there. Yes. Good. Long. Okay, a millisecond is a long time relative to the speed of a processor, so it makes no sense to have the process hold up the processor while you're waiting for that slow operation. Now, by the way, I'm probably going to make sure you guys don't ask the following question at an exam. This happened in 162 a few years ago. We have an exam, and somebody raised their hand, and they said, and then the TA went up, and the TA came back, and he had this very strange look on his face. He said, yeah, that person just asked me whether a millisecond was shorter or longer than a microsecond. Okay? So, if you have that question, look it up, because I might actually ask something like that at some point, because you should know your units. But anyway, millisecond is 1,000th, right, of a second, and that's actually very long compared to nanoseconds, which are the typical cycle time of a processor. And a good rule of thumb is it takes about 1 million instruction times to read something off a disk. So you better put that process to sleep, because you don't want to lose you don't want to waste 1 million instructions worth of stuff waiting for that disk to come around. Okay? 1 million is big. 1 million's bigger than 1,000. Less than 1 billion. Okay, good. You've learned something new today. So, writes, so reads, we put things to sleep. Writes are also interesting. When you write to a file system and you return from the write, the system call returns, the data is not necessarily on the disk. It's buffered in memory in the kernel. Okay? Wow. Writing to a file doesn't make it permanent. If your machine were to crash at the exactly wrong time, you would lose your data. Okay? Unless you have the file opened in a special way or you execute a flush operation to make sure it's flushed actually to disk. Okay? So the kernel is doing a lot of buffering and virtualization inside there of these devices and the user program. So keep that in mind when you think you have a handle on exactly what's going on, okay? And there's an explicit close operation, there's an explicit flush operation, and so on. And so there's many layers to I.O. devices, and we're only going to get to a couple of these today, but I wanted to show you a few of them. Up high is the application, and here in the application, you might actually execute an fopen for a stream or buffered file, and what you have is you use the high-level C library, and it invokes low-level I/O system calls, and those talk to the file system, which has things like buffering, and the file system talks to device drivers. And so if you're up here and you're reading from a file, what's actually happening is you go into the library, it takes a system call, it goes into the file system, discovers that it doesn't have the data you want in its memory, it invokes a device driver, which starts a DMA operation off the disk, there's an interrupt a little bit later, it comes into the device driver, comes back to the file system, puts it in the buffer cache, returns from the system call, comes back out of the low-level I/O into your library, back into your application, and voila, you got your byte. Okay? And I apologize to the person attempting to actually type in the front row. We'll do that again. So what is a file? You could say, Professor talks really fast. So a file is basically a named collection of data in the file system, and the file data can be anything, okay? Text, binary, objects. It could be a database. And the thing about this uniform interface is all of these things are treated the same. So when you put an application on top of a file, and that application happens to be using formatted database data, nothing in the kernel has to know, because it's the database is doing its own reads and writes, and that data is getting passed up, and it's the database that's interpreting. Okay? Now, a file is basically a collection of data. A directory is really just a file whose sole job it is to map between names and other directories or files. So a directory is really just a special type of file. And basically the paths that you are used to, home, /ff/cs162/public// this is a typical file name. And each, the main slash is the root file system. Home is a name that's inside the root directory that points to this directory, which happens to have FF in it, which is a name inside a directory that points to the CS162, and so on and so forth. And eventually, we get a directory that is the FA14 or whatever. I should have changed this to SP15. And that has a pointer to inside of it is actually a bunch of file pointers like index.html, and that points to an inode, which points to the structure of the file, and so on. Okay, so that's all a directory is a set of files that are linked together that point at other directories or files. Okay, and the high-level API for streams of data is really about operating on sequences of bytes regardless of whether they're text or data. And so if you look in here, typically something you're going to get used to is this. Here's an fopen call where you give the file name, which is a string, and then you sort of say what is the mode to open that in, and what returns back is a file descriptor. And once you have that file descriptor, then you can use it in something like an fclose operation to close the file, or a read operation to read, and so on. Okay, and here are some of the modes: read, write, etc., binary, so on. There's a lot of interesting modes. And if you fopen, do some writes, and close, of course, don't forget to flush. You've seen these written around campus in various places, right? So, very important. Okay, so process typically has a current working directory. Bear with me for a moment. I just want to say a couple of things before we finish. So the current working directory is the process's notion of where it is in the file system, and as a result, you can either use absolute paths or relative ones. And so because there's a current working directory, if you go to fopen quote index.html with no slashes, what does that do? It grabs the current working directory, appends index.html to it, and that's the file you actually open. Okay? So there are, by the way, standard in, standard out, and standard error are standard streams. Standard in is for the keyboard input typically. Standard out is for the screen output. Standard error is for errors. And so as a result, this that I showed you earlier, find piped into grep, piped into WC, this little pipe symbol is actually saying something pretty sophisticated. The shell is constructing three processes, find, grep, and WC. It's connecting the standard out of find to the standard in of grep. It's connecting the standard out of grep to the standard in of WC and so on. And so those are all linking together. And the programs themselves are reading and writing from standard in and standard out. And you can mix and match them any way you want in these pipe symbols. How many people have ever done that before with the, okay, good. All right, so that's the way you think of this. And so there's a lot of interesting things in this Stream API, which we'll pick up next time. But for instance, once you have a file descriptor where you've opened a file, now you can do things like putting a character, fputc, putting a string, fputS. You can do reads and writes of whole blocks where you sort of say how big your block is. You can do formatted prints. Okay. So, in conclusion, we finished up really pushing on processes, which is, again, it's the container. A process is an execution environment with restricted rights. It has an address space and one or more threads. Try to keep that in your mind. We talked a bit about interrupts, which is a hardware mechanism for regaining control from the user. And we talked about native control of processes, fork, exec, wait, signal. And we started talking about basic I/O. We're going to pick that up next time. Don't forget the drop date is Friday. If you're going to drop, do so a little earlier so people off the wait list can get in. But have a great weekend. I'll see you on Monday when the homework is due.